Welcome back, everyone. So in this video, we're going to talk about how we are going to examine, read, and do semi-log plots. So the big idea with semi-log plots is we're looking at another way to read exponential data. So especially when we're using exponential data like in the very early times or even in the very later times, like when data gets kind of scrunched together or it's extremely far apart, it can be really difficult to be able to, it can be really difficult to actually display that data graphically because it's going to start out very small, but then grow very quickly, and it's just going to be very difficult to actually understand what's really happening in that sort of visual graph. So what was developed is called a semi-log plot. So what's going to happen is we're going to take your y-axis, and what we're going to do is we're going to logarithmically scale the y-axis so that we can read our exponential data in a different manner. So when we logarithmically scale the y-axis, we can actually take a better idea of what's happening in these earlier points or even in the later data when the spread becomes even more. So over here on the right side, this blank graph right here is what we're going to call a semi-log plot. So just to kind of start off by reading a semi-log plot, we're going to look over at the y-axis. So as you hopefully can read and notice, from this first tier over here, we're going from 1 to 10. So we're starting off with 10 to the power of 0, and then we're going to go up to 10 to the first power. So all the tiers within this first layer is going to be counting starting at 1. So then we would have 2, 3, 4, 5, 6, 7, 8, 9, and then up to 10. So of course they're going to get, because of the scaling, they're going to get more scrunched up together as we get closer to the next power of 10. So in this first tier, we're going to be counting by 1. And then in the next tier, we're going from 10 to the first power up to 10 to the second power. So in this case, in this next tier, now we're going by tens. So we're going to have 10, then 20, 30, 40, 50, 60, 70, 80, 90, and then up to 100. So this next tier, we're actually going to count by tens. And then that pattern is going to continue. So up to the next tier, now we're going to go from 10 to the second power up to 10 to the third power. So now instead of counting by 1 like we did in the first tier, and then by tens in the second tier, hopefully you can kind of see the pattern, now we're going to count by 100 in the next tier. So this first level here is going to be 100. Then we're going to go to 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. So in this upper tier here, we're going to count by 100. So what's also really important to notice that many people have that misconception of is this first tier right here. This is actually going to start at 1 because we are starting at 10 to a 0 power. We cannot plot 0 in terms of a y value. That value just doesn't exist on a semi-log plot. We're going to start at 1. So getting that kind of idea under wraps is going to be super important. So now we're actually going to graph the following coordinates. And then you need to make sure that you're labeling them accordingly. So the first point that we want to label is going to be 0, 20. So horizontally, I'm just going to go at 0. It's vertically that we can't have 0. Horizontally, we can have 0. And then we're going to go up to 20. So in this first tier, we're counting by ones. So this is going to be from 1 to 10. So I can't be in this tier. But in the next tier up here, we're counting by tens. So remember, this is going to be the start of 10. And then the next tier up, that would be 20. So up at 0, 20, this would be point A. So you don't have to put the actual coordinate itself. As long as you put the letter, I'm happy. But writing the coordinate would just be kind of a bonus. So now if I look at 1, 300 for letter B, so I'm going to go to 1 horizontally, and then I want to go to 300 vertically. So I know 100 is going to be at this tier, and then 200, 300. So that means my point right here is going to be point B. And then this would be 1, 300. All right, and then point C, now we have 2, 2. So 2 horizontally, and then I'm going to count up. So remember, we're starting at 1 on this first line right here. So then 2, 2 is actually going to be right here. And then for part D, now we have 3 comma 15. So 3 comma 15, I'm going to go to 3 horizontally, and then I want to go up to 15. So 15 is going to be in between 10 and 20. Now, if you look at how the scaling is, we're going to get a little bit scrunched as we get further up. So that means we're going to be a little bit closer up to 20 based on the scaling. So I'm going to put it a smidge more than halfway. And then I'm going to say this is going to be point D, which is going to be 3 comma 15. Okay, and then your next point, we have point E, so 4 comma 250. So I'm going to go to 4 horizontally, and then we're going to go up to 450. Nope, not 450, 250. So we have 100, 200, and then this is 300. So I want to be in between 200 and 300. So just like before, I want to be slightly above based on the scaling. And then this would be point E. And then this is going to be 4 comma 250. And last but not least, now we have point F, which is going to be 5 comma 1. So I'm going to go to 5 horizontally, and then we start at 1. So that's going to be right at the lowest point we can go. So this is going to be point F, which is 5 comma 1. So once again, just to reiterate, you don't have to put the actual coordinate itself if you don't want to. I mean, I would say it's a bonus if you do. But the letter is what's really important. Because if you just put a bunch of individual points on a semi-log plot, your instructor, your teacher, or whoever's reading, we're not going to be able to distinguish which point is what based on a group of points. So if you don't label your points, you would not be awarded any points or anything if it was a FRQ. So now moving on. So when we logarithmically scale the vertical axis, we're not actually going to change the value. We're just going to change the way that the data is presented to you. So that's kind of the big idea with what we're doing with semi-log plots. So with the second set of points, it's the same idea. It's just we're going to incorporate decimals into these values as well. So that's really for the x-axis, but we can also do that on the y-axis as well. So if I look on the x-axis, hopefully you'll see that we have these little hash marks. So the hash marks, based on this graph and based on this scale, we're going to count by 0.2. So this would be 0.2, then 0.4, 0.6, 0.8, and then 1. Then 1, 0.2, 0.4, 0.6, 0.8, and then 2, 0.2, 0.4, 0.8, I can't count, 6, 0.8, and then so on and so on. So if I want to plot 0.4, comma 40, so I'm going to go to 0.4, and then what helps me is I like to draw the vertical line on my iPad, and then I'll go to 40, which is going to match. So this is going to be 10, 20, 30, 40. So that means I want this point right here, and then I'm going to label that point G, and get rid of that vertical line. And then point G, that is going to be 0.4, comma 40. Okay, and then it's the same idea as before, so I would let you guys go ahead and try those, but we're going to move on to the next idea. So after Mr. Vandersheet displays another one of his math puns to the on his whiteboard outside his classroom, it begins to spread around the school. The number of people, P, that have read or heard the joke after T minutes is graphed on the semi-log plot where the vertical axis has been logarithmically scaled. Which of the following functions could be the model for P? So what we're going to look at is we're going to start off with just your semi-log plot in general. And we want to look to see what English is hard. We're going to see what identifiable points we can find. So if I look at this first coordinate over here, so I know this coordinate right here based on the semi-log plot is going to be 0, comma 2. And then if I look at the next point, so this is going to be, we have 1, 2, 3, and then 4. So this would be 1, comma 4. And then based on the next point, so this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 2, comma 8. And then these other points over here that we have, since they're kind of in between, we can't really assume what those points are going to be. We can kind of make an estimate. So if I just look at my data points over here to go from 2 to 4 to 8, so that means I would multiply by 2. So I'm going to make an estimate and say, well, this is probably going to be 3, comma 16. Well, that's in between 10 and 20, so that could be, which means if I just keep doubling, then that would be 4 comma 32. And 32, that's in between 30 and 40, so that point also kind of checks out. And then we would have 5 comma 64, and that would be in between 10, 20, 30, 40, 50, 60, 70. So that also does kind of check out. So what's in pink is what I'm going to kind of make some assumptions, but we don't know for sure. So looking over at your options over here, we're looking to see which one potentially could be our semi-log plot. So if I look, so the first equation here, we have 2 plus 2x. Well, your semi-log plot is going to linearize. Your semi-log plot is going to linearize exponential data. So what that tells me is this equation is not going to be it. This is just a linear equation in general. So really what we're looking for is we're looking for an exponential function that's going to follow this type of pattern. So with that in mind, I know it can't be C either. We're not looking at a logarithmic equation. So a semi-log plot is we're looking to vertically scale an exponential equation. So I'm looking at either B or D. So then to be able to give me an idea of which one I'm looking for, I'm actually going to plug in the points and see just which one works. But another idea that could also work is I'm actually going to look at my y-intercept, which in this case is 2. My y-intercept of an exponential function tells me that that would be my a value. And then if you want to look at the multiplicative rate, so if I go from 2 to 4 and then to 8 and then to 16 and so on, we're multiplying by 2 each time. So what this tells me is that my b value in my exponential function has to be 2. So if I look at a general exponential function rule, I'm looking at y equals a times b raised to the x, which means we're looking at 2 times 2 raised to the x. So that means we're looking at the function for option D. So you could also plug in points to B and or D, and you can see which one it works for. So I will say, even when you plug in points, just to check it, D is going to be your best option. So now looking at 4, so the table gives selected values for a function f. Which of the following graphs could represent these data points in a semi-log plot, where the vertical axis is logarithmically scaled? So especially on the AP Precal exam, they're not going to tell you necessarily or directly that the y-axis is vertically scaled. They're just going to say the vertical axis. So I've noticed that when I kind of look at different problems that AP Classroom presents. But so just look at your data. So first off, they're going to logarithmically scale the vertical axis. So just take a look at your given graphs, and we're going to look to see which one of these has been scaled correctly. So if I look at option A, your vertical axis is not even scaled by a base of 10 or even just logarithmically scaled. So A is out. B, we're going from 1 to 10, and that tells me that we're being logarithmically scaled. So B could be a contender. If I look at C, once again, my axes are not, or my vertical axis rather, is not logarithmically scaled. So C is out. So my only options are B or D. So now you're going to look at your data. So if I'm looking at data points that have 40, 60, 90, 135, and 203, if I look at B, we only go from 1 to 10. So that doesn't even fit the first coordinate. But if I look at D, your options, we're going from 1 to 10 to 100 to 1,000. So the first value of 40, 60, let's look at the first set. 40, 60, 90. So we have 10, 20, 30, 40, 50, 60, 70, 80, 90. So D is going to be your best option in this case. B doesn't even go up to 40, so the first point doesn't even work. All right, now looking at this next set of problems, now we're going to actually be given a semi-log plot, and what we want to do is we want to write a linear model in log form, and we're going to write an exponential model that models this data. So in linear model for these problems, it's going to be in the form y equals log base n of b of times x plus log base n of a. And then that same, the same components of that equation can also be used to write the exponential model. So starting off, I'm going to actually come back up here to this model. So your n value, your base, is actually going to be the base of the logarithmically scaled vertical axis. So I will say in all the problems that I've seen us do, we're always going to use a base of 10, which means that typically your n value is going to equal 10. So I can't speak for every year that we're not going to always use base 10, but for the problems I've seen, we're typically just going to stick to base 10. Okay, and then we're also going to look at your equation setup in general. So as you hopefully noticed, this is going to be in the same form of slope-intercept form of just y equals mx plus b, where your m value, of course, is going to represent your slope. And then your b value up here, of course, is going to represent your y-intercept. So we're going to kind of translate the same idea over to your linear model for your semi-log plots. So your log base n of b right here, this is going to represent your average rate of change. So notice how I'm saying average rate of change and not slope. Slope is going to refer to a linear equation. Average rate of change refers to how are we changing from one point to the next in a specific equation. So average rate of change also works for nonlinear equations. Slope typically only works for linear equations. Okay, and then your log base n of a, just as mentioned before, this is also going to be your y-intercept. So looking down here, I want to first identify the points on my semi-log plot. So when I look at these points, I can see my first point is going to be in between 10 and 100. So that means in this tier, I want to count by tens. So this would be 10, 20, 30, 40. So my first point here, we're looking at 1, 40. And then my next point that I'm going to look at, we're still in that same tier, so 10, 20, 30, 40, 50, 60. So this would be 2, 60. And then really those are the only 2 points you need in order to write the equation. So like this one up here, it looks like it could be 90. This one's going to be a little unclear specifically what this one could be. And then this one up here looks like it's going to be 200. But of course, we also don't want to assume. But these points, these pass clearly through those specific values. So I'm pretty confident about these values. Okay, so what we want to do, once we identify 2 points from your semi-log plot, first thing I want to do is I actually want to find the average rate of change. So I'm going to start with the average rate of change between these 2 points. So I'm going to find f of 2 minus f of 1, and that's going to be over 2 minus 1. Now, because we're working with a semi-log plot, you're going to have to logarithmically scale the y values, which means when I plug in the output values for f of 2 and f of 1, I'm not just going to write in 60 and then 40, respectively. What you're going to have to do is we're going to do log of 60, then minus log of 40. And then that's going to be over 2 minus 1, which, of course, hopefully is just 1. Okay, and then I'm going to be left with log of 60 minus log of 40. And then I'm going to use log properties, and I'm going to condense. So I'm going to rewrite it as log of 60 over 40, which, as you simplify, is going to give you log of 3/2. So what we just found is the average rate of change. Now, the average rate of change is log of 3/2, not just 3/2. But what this does tell me is that your b value is equal to 3/2. So now that we have the b value, now I want to go back up to my model up here, and I want to plug in another point so I can solve for my a value. So I'm actually going to plug in 1, 40. So I'm going to write out my model. So we have y equals log base n. So really we're in base 10, so I don't have to write the 10. So it's going to be log of your b value, which is, here, let's just start with the model, actually. Go away. So So here's your model. So now I'm going to plug in for your b value, which we said was 3/2 plus log of a. And now what I'm going to do is I'm going to plug in a point. So I'm going to plug in 1, 40. But remember, because we're logarithmically scaling the y-axis, I have to plug in log of the y value. So this is going to be log of 40, and that's going to be equal to log of 3/2 times my x value, which I'm plugging in 1, plus log of a. So now I'm going to rewrite the right side here. I'm going to condense it into a single log. So I'm going to multiply the arguments together. So 1 times log of 3/2 is just going to be log of 3/2. So I just have the 3/2 in the a value. So I'm going to rewrite this as log of 40 equals log of 3/2 a. And now that we have condensed logs with the same base on both sides, now I'm going to set the arguments equal. So I'm going to have 40 is equal to 3/2 a, and then solve it just like you would an algebra equation. So multiply both sides by 2 and then divide both sides by 3. So that means we're going to have an a value that is 80 divided by 3. Okay, so now I have my a value and I have my b value. So now I'm ready to write in my linear model and my exponential model. So I know my a value, which is going to be 80/3. And I know my b value, which is going to be 3/2. So when I write this as a linear model, we're going to use this model up here. We're just going to plug in the a and the b value. So that tells me my linear model is going to be y equals log of 3/2 times x plus log of 80/3. And then your linear model, we're just going to write it using your a times b raised to the x, and it's using the same a and b values as before. So this is going to be y equals 80/3 times, let's do parentheses. Let me rewrite this. So 80/3 parentheses 3/2 raised to the x. So that would be your first problem. So now down below, we're going to do the same idea, but we're just given a different semi-log plot. So starting off, once again, I only need to find 2 points. So I'm going to look for some clear, concise points that I can use. So for this first one, we have a tier of 100. So I'm going to count by hundreds in this tier, which means this point would be at 200, vertically at least. So then we have 1, 2, 3, that's a 3. So that means this is going to be 1, 200. And then my next point, it's going to be at 2, 100. So it looks like we're cutting in half. So that means this would be 10, 20, 30, 40, 50. Yep, so it looks like we're cutting in half. Which means this one likely is going to be 4, 25. Likely. So let me actually do a different color because I don't know for sure. Sure, why not? All right, so I'm just going to use the first 2 points because I know those are pretty definitively those points. So once again, we're going to start with the average rate of change. So your AROC. So we don't have like a f of x or g of x equals, so I'm just going to use f of x by default. So f of 2 minus f of 1 over 2 minus 1. Then once again, because we are logarithmically scaling the y-axis, we are going to have to plug in log of whatever the y values are. So I'm going to do log of 100 minus log of 200, and that's going to be over 2 minus 1, which is just 1. And then I'm going to go ahead and condense. So we're going to have log of 100 over 200, which means we're going to have log of 1/2, which tells me that my b value in this case is going to be equal to 1/2. So now that I have the average rate of change, now I'm ready to actually go through and find, well, let me make something pretty clear. The log of 1/2, this is your average rate of change, but we're saying that the b value itself is 1/2. So now that we have that, now I'm going to go ahead and plug in. So we're still using base 10, so log of b times x plus log of a. So I'm going to plug in for my b value, so we're going to have log of 1/2 times the next value plus log of a, and then I'm going to plug in a point. So I'm going to go ahead and just plug in 1,200. So once again, I'm going to plug in log of 200 since we're logarithmically scaled on the vertical axis, and that's going to equal log of 1/2, which is your b value, and then your x value in this case is going to be 1 plus log of a. So 1 times log of 1/2 is just going to give you the log of 1/2. So I'm going to rewrite this as log of 200 equals log of 1/2 plus log of a. And then on the right side, we can condense. So I'm going to have log of 200 equals log of 1/2 a. So we can multiply those arguments. Now that we have condensed logs with the same base on both sides, I'm going to set the arguments equal. So now I'm going to have 200 is equal to 1/2 a. Multiply both sides by 2. So we're going to get an a value of 400. So now that I have my a and my b value, so I know my a value is going to be 400. I know my b value is 1/2. And based on this setup, I know my linear model will read as log of 1/2 times x plus log of 400. And then my exponential model is going to be y equals my a value, which is 400, times 1/2 raised to the x. Okay, now for 7 and 8, I would invite you guys to try these two on your own. We were even a little bit more generous and we actually labeled the points for you. So I would say try these on your own, but I will go ahead and write in the linear model for you for this first one. So the linear model, when you finish it, hopefully you're going to get log of 5 times x plus log of 3, which means your exponential model will be 3 times 5 raised to the x. So we'd have an a value of 3 and a b value of 5. And then for your last one over here, same idea. I'm going to give you guys time to try it on your own, but so you can check it, your linear model is going to read as log of 1/4 x plus log of 2048 with your exponential model being 2048 times 1/4 raised to the x, and then your a value being 2048 and a b value of 1/4. So definitely make sure you do those, check them. And yeah, these could hypothetically be on the calculator or non-calculator section. I will say I haven't touched a calculator at all throughout this entire video. So odds are it's going to be on the no calculator section, just giving you kind of a heads up. So make good choices.